Come with me for a moment. Let's try to see the universe through a new pair of eyes. Imagine you are young Albert Einstein, not yet the icon with the wild hair, but a curious mind working in a Swiss patent office. You look at a clock tower and wonder, what would happen if you could ride on a beam of light? Would you see time itself stand still? Most people see the world and accept it as it is. A clock is a clock. A ruler is a ruler. But Einstein saw a universe full of deep, unanswered questions hiding in plain sight. He wasn't afraid to challenge the most basic ideas we all take for granted. This wasn't rebellion. It was a profound form of curiosity. His journey began not with complex equations, but with simple thought experiments. He would imagine himself in impossible situations, chasing a light wave. These weren't just daydreams, they were powerful tools for prying open the secrets of reality. He asked questions that seemed almost childlike in their simplicity, yet they struck at the very heart of physics. What does simultaneously even mean? For centuries, physics was governed by the elegant laws of Isaac Newton. Everything made sense. If you were on a train throwing a ball forward, you would simply add the train's speed to the ball's speed to know its true velocity. Simple, logical, intuitive. But a ghost haunted this orderly mechanical universe, the speed of light. Experiments in the late 19th century revealed something deeply strange. No matter how fast you are moving or what direction you are going, light always travels at the exact same speed, about 671 million miles per hour. It's a cosmic speed limit that nothing can break. This was a colossal problem. Think about it. If you're in a spaceship traveling at half the speed of light and you turn on your headlights, you might expect the light beam to travel at 1.5 times the speed of light. But it doesn't. It still travels at the exact same unchanging speed. This fact broke all the rules of classical physics. This single inconvenient fact was the thread that, when pulled, would unravel our entire understanding of space and time. So, what is this space-time that Einstein imagined? Think of it as a giant, flexible sheet of cosmic fabric. It has 4 dimensions: length, width, height, time. Everything in the universe exists and moves within this fabric. Before Einstein, we thought of space as a static stage. Time was an independently ticking universal clock, the same for everyone. But Einstein showed space and time are not separate. They are woven together, inextricably linked. You cannot affect one without affecting the other. This is where time dilation comes from. It's a direct consequence of the constant speed of light. Imagine 2 friends, one on Earth, one blasting off in a super-fast spaceship. For the astronaut traveling near light speed, time itself slows down. This isn't a trick of perception or a problem with their clocks. Time itself passes more slowly for them. When the astronaut returns after what felt like a few years, decades have passed for their friend. Space becomes flexible too. Objects at very high speeds appear shorter along their motion. Length contraction. From a stationary observer, the spaceship looks squished. We each have our own personal clock and ruler. Einstein's special relativity was brilliant, but it was incomplete. It didn't include gravity. For more than 250 years, Newton's law of universal gravitation had reigned supreme. Newton described gravity as an invisible force, a mysterious pull that every object exerts on every other object. It was, honestly, a good description. It could predict the orbits of planets and the trajectory of a cannonball. How could the sun, millions of miles away, reach out with an invisible hand and pull on the Earth instantaneously? Einstein spent 10 years wrestling with this problem, and his solution was even more profound than special relativity. In his general theory of relativity, he proposed something extraordinary. Gravity is not a force at all. It is the consequence of mass and energy warping or curving the fabric of spacetime. Think of that cosmic fabric again, our 4-dimensional sheet. Now place a heavy object like a bowling ball in the center. The fabric will dimple and curve under its weight. This curvature is what we feel as gravity. Massive objects don't pull on other objects. They simply tell spacetime how to curve. Now imagine rolling a small marble near the bowling ball. That is exactly what planets do. The Earth is just following the curve in spacetime created by the sun's immense mass. It thinks it's traveling in a straight line through a curved space. Even light, which has no mass, must follow these curves. Einstein's ideas didn't just add a new chapter to the textbook of physics. They tore up the old book and started a new one. The consequences of his theories are all around us, shaping the world in ways he could have never predicted. General relativity is not some abstract, esoteric concept. Your phone's GPS, for example, relies on it every single day. The satellites orbiting Earth experience time slightly faster than we do on the ground because they are in a region of weaker gravity. Without correcting for this relativistic effect, your GPS would become inaccurate by several miles within a single day. They predicted the existence of black holes, objects so massive that they curve space-time to an infinite degree. They predicted that the universe itself is not static but is expanding, an idea later confirmed by Edwin Hubble. And they predicted the existence of gravitational waves, ripples in the fabric of space-time, created by cataclysmic events like the collision of two black holes. A century later, in 2015, we finally detected these faint echoes from a cosmic collision, hearing the universe in a brand new way. The legacy of Einstein is more than just equations and predictions. It is a testament to the power of human curiosity. He taught us that the universe is not always what it seems, and that our common sense can be a poor guide to understanding reality. So let's keep that spirit of inquiry alive.